Okay, so good morning everybody, welcome back. A few notices. On the website I updated the calendar, the schedule of the lessons. This was already there, so we will have lessons on Monday next week, not on Tuesday. This was already there from a long time. Because I think Tuesday afternoon you will go somewhere with Professor Iori. We have 2 additional lessons. Okay, I tried to keep you free of this early slot on Friday, but I can't. I actually need to do a specific amount of hours. So we will need for sure to do lessons on November 29th and on December 6th for the first 2 hours of Friday. And the lesson on the 3rd of December, it will be actually the whole lesson or part of it. It is not fully clear now, but I will update you. We will have a speech from Credem, which is a local company. It is a bank company, okay? Probably many of you know already Credem if you're here in Reggio or in Modena. We will have, me and Professor Monica will advertise this seminar also outside of the specific class and of the master's degree. It is a seminar that can have potentially a wide interest, so we will try to advertise to many other students. It will be obviously in English as the course, and it will be basically about applying data science to a specific domain. So I strongly advise you to participate in the seminar because you will see actually, you will have a quite good feedback about how actually to put in practice some of the things we see in the course in a specific real-world example, which is this bank system. Okay, more on the seminar will come. Okay, we will have some sort of flyers and more information will be published also on the website of the course, on the website of the Digital Automation Engineering Master's degree. It will be, again, I'm not exactly sure, but I think it will take at least 2 hours, and then maybe we can call it a day, or we can have some normal lecture afterwards or before the seminar. So these are the updates. The updates are basically in bold. Okay, so it's easy to spot them. And now instead we continue with our actual contents. And now we switch a bit topics and we will start a great, let's say, adventure in the realm of machine learning. This will actually be the greatest part of the lectures, as you probably have seen from the slides I already put on the website and from the previous year. So we will start talking about machine learning, basically. Okay, so the idea of teaching the machine to do something or to automate some task. This first batch of slides will be more or less an overview of the whole machine learning fields. Then we will go in the details of some of the approaches. Also, this part obviously will have code examples to make it clear that the concept that we will see have a direct application in code. We will see quickly these examples in our lessons, and as I already said, if you want to know more about the specific example, just send me an email or if you need help understanding some of the examples. Most of these examples, as it was the case for plotting examples, will be using external libraries. Okay, we don't reinvent the wheel in this course. If there is a tool that is already ready for use to teach the machine to do something, so to do linear regression, to do supervector machines, to do clustering, to create a neural network, we will use it, okay, without questioning too much what are the inner workings of the library. So, first of all, what is machine learning? Well, a very first definition was quite dated. in the lifespan, in the usual lifespan of computer science, because it was due to Alan Turing. And one thing that he said that is quite true, I would argue that it is more true the more that this research field progresses, that when we teach a machine to do something, most of the time we don't know exactly what's going on behind the scenes, okay? And this is even more true with deep reinforcement learning. Obviously, we as engineers know perfectly how the neural network works, how every single artificial neuron works, every single layer of the neural network works. We designed it. But this is the classical example in which the whole is much more than the sum of its parts. Okay, so what's going on, how exactly the machine is learning, it may be not entirely true. And this is even more so in a very recent example, for instance, with large language models, in which researchers are still trying to understand what exactly is going on. Then a more, let's say, formal definition is due to Mitchell. A computer program is set to learn from experience. Okay, this is more or less, this applies to the whole machine learning field, which is a huge field. We will see that there are at least 3 very big macro areas within machine learning. Learn from experience, E, with respect to some class of tasks, T. Sometimes this class of tasks gets reduced to a single task. And performance measure, P, this is very important, because we need to measure whether the machine is actually learning or not. If its performance, measured according to P, in this class of tasks T, improves by giving the machine more experience. Usually, or at least in a first, let's say, approximation simplification, you can simply equate experience with data. Okay, so something about the sentence, just throw some data at the computer, something is true. Okay, throw more data to a computer and usually learning is better. Obviously, machine learning is not, since a few years, a very hot topic in artificial intelligence in general. It may seem that artificial intelligence is all about machine learning. With Professor Monica, you should instead have understood that no, it is not the case. Okay, there is also artificial intelligence which is not machine learning, or that is not only machine learning. Why so many big companies are investing plenty of money in this? We already, to some extent, touched the argument. They have lots of data, lots and lots of data, and they need to do something with that data. Okay, otherwise data sits there. It is a sort of wasted potential for increasing revenues, basically. Okay, the biggest companies that are playing with machine learning are actually for-profit companies. Okay, even OpenAI, that should have been more or less open, non-for-profit organization, quickly became a sort of company. And we have examples of machine learning in our everyday life, and since many years. One of the first earlier examples of applied machine learning has been in the email domain for classifying incoming mails, whether they are, let's say, genuine mail or simply spam. Okay, and it is difficult to define spam, because what may be spam for me, maybe it's not spam for you. It depends on the domain you're working on. Obviously, I get a lot of spam, like published with this journal, whatever, so it's not easy. This is one of the first examples. Forecasting stock prices, okay? If you want to get rich, one way is try to be good at forecasting stock prices. The stock market, we already mentioned this, is also one of those application domains in which algorithms are truly deployed on an everyday basis, and most of the trading that goes on is actually made by algorithms and not people. Okay, simply because the pace of trading is so quick, it's so high, that and algorithms is usually a better trader than a human. Let's say, maybe not actually making a diagnosis, but for sure assisting doctors in making diagnosis. There is lots of machine learning in there, okay? This is not only, obviously, one big example, IBM Watson, but even on a smaller scale, many simply computerized applications that doctors use in their everyday routine have some sort of artificial intelligence in them to assist the doctors. Recognize digits. This is what can be called, for instance, OCR, optical character recognition. Teaching robots to do stuff. This is a humanoid robot just because it's usually nicer, prettier, but industrial robots as well. Okay, a robotic arm that needs to work in an assembly line. This is something that is really actual, I would say, since a Nobel Prize was won basically with work in this field, designing new kinds of drugs or synthetic molecules to achieve particular effects. Textual translation, also this is not so recent, it is a few years that actually not only Google Translate but other translation services are quite good at translating text. Converting text to speech, again, we are more or less used to having our personal assistants in our smartphones, okay? A big part of that personal assistant is employs some sort of machine learning, recommending movies, okay? Netflix, Prime, Disney Plus, whatever you can think of. That's another place where machine learning is used. Captioning images. These examples are a bit old nowadays. Also, you will probably know that even creating images, creating videos, there are actually also quite striking examples nowadays of AI, and in particular generative models used to correct or improve how it is called, the lip syncing people speaking in a different language in movies, no? Doppiaggio in italiano, I don't know exactly how to translate it. So these are all examples, and obviously also more, let's say, maybe entertaining purposes, but behind this entertainment there is lots of work and lots of potential applications. So AlphaGo, chess, they are all examples of software playing video games or board games. As we said, machine learning is a huge field, and it may roughly be divided into 4 subfields. And beware that each of these subfields is huge, okay, on its own. In this course, we will mostly see supervised learning. We will also see a bit of unsupervised learning. I don't know if we manage to see a bit of reinforcement learning. This will be a novelty with respect to previous year's edition, but since it is one of the fields where I'm doing research and it is appropriate, if we can, we will at least see an overview of it. So what is supervised learning? Supervised learning is basically about finding patterns in data, a mapping between input and output variables, in which between independent and dependent variables, okay, given labeled data. What is this labeled data? It is data for which I already know the association that I want to learn, okay? They are examples of the mapping that the machine has to learn, okay? So, for instance, I don't know, predicting the chance of raining on a particular day, given weather data such as, I have no idea, the temperature, humidity, clouds, stuff like that, okay? So, having labeled a data observation means that we built a dataset of, I don't know, 1 year of weather data. And for this 1 year of weather data, we have both the so-called observed variables, the independent variables, like the humidity level, the temperature, whether there was fog, the kind of clouds, whatever you can think of. And we also have the prediction targets, the dependent variable also called. So we know for this 1 year of past data, whether in that specific day, with that specific independent variables, the clouds, the temperature, the humidity level, whether actually it rained that day, okay? Or how much did it rain. So our dataset is both the data that we want to base our prediction on and the actual ground truth, okay? Whether our prediction target for that day, what was the actual event. The task of supervised learning is to build a function, basically. Usually not completely build the function from scratch. Usually you already choose what function and you only need supervised learning. You only need the machine to learn the parameters of this function. And you want to learn a function to do the mapping. The function must be able to predict our target variable, our dependent variable, given some observed variable, some independent variable that it never saw before. Okay, that's our objective, for which we don't have the actual prediction targets. At least we don't have them when we want the prediction. Okay? It's like predicting the chance of raining for the next week. Now I don't have the ground truth. I don't have the actual prediction. Okay, I don't have whether it will rain in this week. So I can try to build a function to predict this week of rain or not. In 1 week, I will have the ground truth. Okay, and I can in 1 week I can evaluate my predictions, were they correct, were they wrong. So these are actually the basic ingredients, all of the ingredients of supervised learning. It is called usually labeled data because for the data for which you have the actual ground truth, these usually are called the labels. Okay, that's just terminology. As we will see, there are many ways to do supervised learning, and the following 2 or 3 batch of slides will actually delve into specific means. There are different methods, and each method has its own issues, and each method may be well suited for a given set of tasks, depending on a few things. Here are the most abstract and the most relevant. The kind of input space, what kind of variables do we have? Okay, it is time-dependent variables. Are they discrete variables? Are they continuous variables? Stuff like that. The same for the output space, so the variables I want to predict, what kind of variable it is. It is a binary variable, will it rain or not? Is it a categorical variable? Will it rain a lot, a few, mild? Or is it a continuous variable? How many millimeters will it rain? Okay, or discrete variables, I don't know. Below 10 millimeters, from 10 to 50 millimeters, stuff like that. The choice that we make for the definition of the function f, as I said, usually you don't completely learn the function from scratch, but you give a shape, an a priori shape, a priori definition for the function, and then you learn the parameters. And the choice is made for actually how to compute this function. There are many ways. Okay, I want to learn, I don't know, I want to do linear regression. Okay, so I want to try to predict data with a linear function relating the x, the data, to the y, the targets, with any linear function, okay? But there are many ways in which I can compute actually that function via learning. Just a few examples that I actually already made. So for the input space, we can have numerical data or attributes, which is also called categorical data. Okay, so for instance, the class in which somebody is enrolled, or the country of origin of people. Can have some sort of higher level logic representation of data. Can be also some structured space. The dataset could also have like complex structures like graphs, trees. We won't go into this kind of stuff. We will keep ourselves limited to simple example in which the input data is mostly numerical or some sort of categorical feature. Output spaces, again, can be in the most complex general case any kind of arbitrary data. Most commonly, it is either a Boolean variable, in which case this is called, the class of tasks is called binary classification. Will it rain or not? Okay. Do I have a given disease or not? Is this mail spam or not? These are all examples of binary classification. Okay. Then we also have multi-class classification. Okay. So again, the output variable is a discrete variable, can be a category or can be a number, but it is discrete and it has more than 2 values. And then we can have also continuous values if, for instance, we want to do regression. Okay. And this depends on the task that you want to do. An example of putting all of this together is classical example, and also probably the most simple example is linear regression. Okay, I have some data, I don't know about what, we don't care. And for doing predictions about unknown data, so we know for instance, the x, but we don't know the y, we simply use a regression line. Okay. In this case, the input space is a d-dimensional continuous space, can be. The output space is a one-dimensional continuous space. The shape of the function, okay, that we want to learn is actually this, a linear combination of features. And we have this sort of how we do this linear combination. If we do linear regression, basically we simply give a coefficient to each of our data and we try to minimize the error between the actual data and my prediction. This is just an example. Okay? So we want to find the parameters that minimize the prediction error in this case, the intercept. This is the intercept of the line, right? Just an example. What is instead unsupervised learning? The name supervised learning should be evident, stems from the fact that the kind of learning is supervised by, let's say, a teacher, an oracle, that knows the correct answer for a given prediction. Okay? The training dataset also has the correct answer about the prediction. So you are able to evaluate, did I miss the prediction or not? In unsupervised learning, you don't have this kind of information. So you try to do something, but there isn't really anybody that can tell you, okay, you're doing right or you're doing wrong. There are no labels, okay? So imagine this setting which you don't have prediction targets. You don't want to predict anything. You only have data, and you want to find some sort, you don't have any mapping to find. You just want to uncover whether there is some relevant pattern in your data, okay? A legitimate question would be, okay, why would it be useful? Well, there are lots of actually implications of this. For instance, you may want to cluster data to find similar data points in groups. You may want to identify important features, for instance, features that affect the most a predictor, a supervised learning model. And you could also try to reduce the dimensionality of your data. If this D is huge, doing prediction, doing supervised learning could become difficult. So for instance, an example of clustering, which is one of the most used unsupervised learning tasks, would be to have all of this data and to try, maybe this data is about, I don't know, customer behavior, so the purchasing habits of your customers in your company. You want to create a new advertisement campaign, and you want to do some targeted advertisement, okay? You don't want to waste money, so you don't want to advertise a product to people that will never buy the product because they are not the right, okay, target of your campaign. So you want to do what is usually called, for instance, segmentation or profiling, okay? Customer profiling, customer segmentation. Try to find groups of customers, maybe with similar purchasing habits. So, for instance, I don't know, families have different habits than single people, okay? Stuff like that. So you can try to do clustering. That is, try to analyze the data looking for patterns. And it may be, these are the actual same data set, extra same plots, but for color. You may find that there are actually 3 customer groups in your customer base. Okay, without doing clustering, you will never notice because, well, okay, maybe here we can see a concentration of points, but there is nothing really, nothing else that tells us this point apart from one of those points. Okay, clustering may help with that. We left, as I said, reinforcement learning open. If we can, we will say a few words in a future lesson. Whatever the problem, even this applies to the whole machine learning stuff, not only supervised or unsupervised. Whatever the problem and the technique you are trying to apply, it is crucial that you can measure the performance. Otherwise, you wouldn't even be able to tell if the machine is learning something useful. Okay, so the most obvious idea, the most naive idea is, okay, let's count the errors. This is not so trivial in practice. Maybe in supervised learning, maybe easier because we have labeled data, but for instance, already in unsupervised learning, counting the errors loses a bit of meaning because we don't really know what an error is, okay? But this is actually the core idea behind more or less all of the performance measures that we have. Let's try to understand how we can create some easy performance, some simple performance measure. Let's say that we have to build a diagnosis system for a pathology, okay? Our system correctly classifies 99.9% of the cases. Can we be happy? This is akin to the statistical inference problem, no? We did, in which having high accuracy didn't exactly mean that the test was good. Well, a first way to measure the performance of, for instance, a classifier, so a supervised learning model, is to build the confusion matrix. This is really one of the most informative things you can do, even if it's simple. This is an example with a binary classification problem, just to keep it simple, but you can easily extend it to a multi-class. Let's assume we only want to know if I have the disease or not. So your prediction will be, okay, you have the disease, no, you don't have the disease. And to check the accuracy of your supervised model, you simply compare this prediction with the actual event. Okay? Obviously, you need a way to measure the actual event. So you build actually what is called a confusion matrix. You put in the rows or in the columns, it's the same obviously. You put in the rows the class that your model predicted. So you have the disease, you don't have the disease, 0 or 1, don't have the disease, have the disease. And you put in the columns instead the ground truth, so the label of the data, okay? Okay, I know that that patient had the disease. So if the patient actually didn't have the disease or has the disease. And then you simply fill in the crossroads. Okay? So if your predictor, if your supervised model predicted the patient to not have the disease and the patient actually didn't have the disease, that's a hit. Okay? Your model took the correct prediction. So we call this a true negative. The patient didn't have the disease, okay, the event didn't happen. This is a true negative. If instead I predicted the patient not to have the disease or the customer not to buy the product, whatever you want, and actually the customer bought the product, this is a false negative. This is a miss. My prediction was wrong. I predicted the customer not to buy the product, but he bought it. So this is a false negative. This is standard terminology also in medicine, okay? When we did the examples about the tests in medicine, that's also the case, okay? With COVID, unfortunately, we know that some tests could be false positive or false negatives. And the other way around. If you predict the customer to buy the product, but it don't buy it, you have a false positive. I predicted the event to happen, but it didn't happen. Or I can predict the event to happen, and the event actually happened. So basically, when you have any sort of prediction, again, you can extend to the multi-class, it's quite trivial. Actually, computing the confusion matrix is a good way to get an overview of the performance. What you want to do, how do you want this confusion matrix to look like? You want to see big numbers in the green cells, okay? And you want to see low numbers in the red cells. So when you have a confusion matrix, you want to have big numbers in the diagonal and small numbers everywhere else. That's it. So it's very easy. Actually, based on this confusion matrix and on these true and false, positive and negatives, you can define 4 very common measures of accuracy. They have their own maybe pitfalls. You need to be careful. You may find plenty of blog posts telling you to be careful about this kind of stuff, but you can define 4 easy measures, and more or less that's the measures that are actually used, okay? You can get sophisticated in the way you actually compute some of the measures, but there is not really much to do. The accuracy is defined based on your correct predictions based on the total sample size, okay? So as you can see here, to compute accuracy, you sum the true positives with the true negatives, so the okay predictions, and you divide on everything, okay? So how many events did I predict right, basically. Then there is another metric, which is the precision, which only cares about positives. How many events I correctly predicted based on only for the positive class. Okay, so only in the case the event happened. And I divide the true positive for the true positive plus the false positives. Okay, this is called precision. Then you have the recall, which is similar, but you actually sum the true positive with the false negative. Okay. Because you want to know, okay, these were my predictions, but how many predictions did how many times I falsely attributed the negative class to my data. Okay, so all of these measures are somewhat complementary. Okay, they give you a different perspective on your prediction. Okay. Whenever you read any kind of paper and they only report one of these metrics, be skeptical. Okay, because they only give you one information. Another, let's say, widely spread measure is called the F1 score, which is basically a combination of the other. It's a combination of precision and recall. This is to try to summarize both measures into one number. Okay. As I said, we did an example with a binary classification problem because it was easy to understand. Can you extend these measures on a multi-class classification problem? Of course, yes. You simply need to expand, okay, your matrix, and you have false positive or false negatives depending on the class you are predicting. But you can define in a similar way these measures, the accuracy, global accuracy. But beware that when you define precision, recall, and F1, this time you need to choose for which class you are computing precision, recall, and F1 score. Why for which class? Because if I have to take the true positives, I need to take the true positive for a specific class. We have the true positive for class A. We have the true positive for class B. And even the negatives are different. If I predict class B and the class was A, this is a false positive with respect to class B, but it is a false negative with respect to class A. So, okay, this is the only complication, which is not conceptual, it's just technical complication. When you go from binary classification, which you have only one of each measure, to multi-class classification, in which the accuracy is fine because you sum over all the data you have, all the predictions. But for the precision, recall, and F1 score, you have actually different. You can have a different precision for this class and a different precision for this other class. We already saw this, okay? In our example of the kidney failures, we have different statistical measure depending on the size of the stone. Usually, based on this number, you compute two graphs, which are easier most of the time to interpret quickly instead of working with numbers, that are called receiver operating characteristic, ROC, and recall precision, okay? Curves. They are just plots of the measures we have seen, okay? So they are nothing new. For recall precision curves, you put the precision on the y-axis and the recall on the x-axis. For the receiving operating characteristics, you put the false positive rate on x-axis and the true positive rate on the y-axis. And why you do so? Because they are very easy to interpret visually. You want, ideally, the ROC curve to be like this. A straight line up to 1 and a straight line up to 1. Okay? For the arrow C curve, you want to have an elbow on the top left corner of your plot. That will be a perfect score. And for the precision recall curve, the other way around. You want to have an elbow on your top right corner of the plot. Again, that will be perfect score. Another metric you can find, which is again a variation of the same measures. Okay, we are just playing with these simple measures. Is instead of showing you the actual plot, they give you a number which is the area under the curve. This area. The bigger the number, the better it is. Sometimes in paper you can read ROC AUC. It means that number is the area under the curve in a receiver operating characteristic curve. Okay? These are just, different ways to represent this very simple method for measuring performance based on the confusion matrix. Obviously, this is quite easy to compute by yourselves, but you can also find plenty of libraries that already give you all these measures for free. But this is really, really easy, obviously, to compute. These are metrics that are mostly used in the case of supervised learning for binary data or categorical data, multi-class classification. Okay? If you want to do regression, usually you don't use this kind of stuff because you have continuous values. Okay? You would have a huge matrix with infinite values. Doesn't make sense. So when you do regression, usually you adopt other measures. Here are just a few examples. There are many others. The mean squared error. So the difference between the predicted value and the actual value, okay, squared and divided on all this average on all the predictions I made. The root of this measure depends on personal preference. And the mean absolute deviation, which is another form in which instead you take the absolute values in different and you perform a mean. We can argue that all of these three measures are more or less the same. They simply measure how far you are from the actual values you want to predict. Why it is important to measure the performance of a model? Exactly because in one of the previous slides, don't make me go back, but in one of the previous slides, we said that there are many ways to build the prediction function. There are many possible models that I may want to try. We will see. We may try linear regression, we may try a decision tree, we may try support vector machines, we may try different forms of neural networks. Obviously, I want to choose the best model, so I need to measure the performance to choose the best model. Choosing the best model is called model selection, which is a very important procedure in machine learning. Also because many state-of-art machine learning models, okay, techniques, and the more they get sophisticated, the more this is true, may depend quite heavily on what are called hyperparameters of the method, of the algorithms, of the model. The hyperparameters are parameters that configure how the specific machine learning algorithms work. Okay? So, for instance, if we want to do regression with some sort of polynomial line, the degree, okay, of the polynomial line we want to employ is actually an hyperparameter of the algorithm. Okay? I need to try probably different degrees and then check what is the line that best interpolates my data points. Maybe it's a straight line, maybe it is a sort of hyperbole or something like that. Okay, a cubic line. So, most machine learning algorithms, models, strongly depends on one or more, usually more, hyperparameters. And you must choose these parameters during training, okay, to make the algorithm work. How do we choose them? Well, usually in general there is no heuristic to choose them, okay? You simply try a bunch and select the one that works better. Obviously, during the years, guidelines, best practices have been developed, but in general, you try them. So the procedure through which we chose the best hyperparameters for a given system is called model selection. Okay? So I want to do linear regression, but I want to choose the degree of the polynomial line. That's a model selection procedure. I will try, I don't know, every degree of the polynomial up to the, I don't know, fourth degree, and then we choose the best model according to some metrics. How can we do this model selection process? Well, first of all, a best practice is to always split the data. I have a whole data set that I can use to develop my machine learning system. Do not use all the data for training. Because if you do that, you don't have data left for actually validating if your model is good enough in your predictions. Because if I have a data set and I train my model on that data set, and then I measure the performance on the same data set, unless I made some mistake, the performance will be high. I mean, I taught my system with given data, and I asked the system to predict that exact data. I expect quite high performance. But usually the goal is that I have some data to train my system, but then I want to apply my system to data for which I don't have, okay, the actual prediction. So, when you have a data set and start to play with the data set with machine learning, already do some split. Partition the data. You need usually at least 3 disjoint sets. Ideally disjoint. 2 of them can also be not actually disjoint, but ideally you will need 3 disjoint sets. 1 training set. This is the subset of the data that I use to actually train my model, that I feed into my model to build this function, this prediction function. Then I need a validation set that I use to select the best model. I train many models, or the same model but with different hyperparameters, and then I measure the performance on a validation set, a subset of data that my models weren't trained on. When you have chosen the best model, perform another validation on a test set that your algorithm actually never seen before, that your best model so far never seen before. Okay? Obviously, doing this may be not trivial, because while doing this sort of splits, at the very least, you should try to maintain the proportion among the classes. What does it mean? Let's assume you are doing binary prediction, okay? Just for the sake of simplicity, okay? I do some random split of the data. I don't know, I have a 10,000 rows data set. I keep the first 7,000 rows as a training set, okay? By chance, in the first 7,000 rows, the only actual class of my data was one of the 2, either false or true. My model won't behave well, because I only gave to the model a partial representation of the whole data. So when you do this kind of split, you should strive to have the same proportion of class representation in each set. I don't know, 50% positive cases, 50% negative cases, more or less the same here, more or less the same here. Obviously, theoretically, the ideal case is that whatever number of classes you want to predict, 2, 3, 4, whatever, you have the exact same representation of classes. I have 10 classes. The 10 classes are represented by 10% of the whole data in each of these splits. That would be the ideal situation. I have 2 classes, 50% in each of the splits. With real data, this is not so easy, okay? Maybe because some of the conditions are rare. Let's go back to the disease example. How many samples you want to have of a rare disease? The problem is inherently imbalanced. You will have many, many more cases of the negative class, people that don't have the disease, and many, many, many few cases of people that have the disease. That's, even by the start, is a difficult problem already, because you have imbalanced classes, an imbalanced representation of classes. So, you should build these 3 data sets out of your data set, and not by chance, but try to keep the correct proportions of data. So the training set, as the name suggests, will be the one that we feed to our algorithms, whatever it is, to learn actually how to build the function f that we want to use to predict. The validation set instead is used to select the best model, and the standard de facto technique for doing validation is called k-fold cross-validation. Okay? There are many ways in which you can do validation, but it doesn't even make sense to expose you to every one of them. That's the de facto standard. Okay? K-fold cross-validation means that actually you don't have disjoint sets between training and validation. The only disjoint is with test set. This is always the case. The test set should not be used for training or nor for validation. Never. Instead, training and validation set can also be based on the same data, given that you perform k-fold cross-validation. What does it mean? You split the data, this data, not this data, into k-sets, whatever you want, okay? Again, a more or less standard hyperparameter has become 10. Tenfold cross-validation has become more or less a standard. You split the data into k-sets, disjoint sets, named folds, okay? In turn, each of these subsets will be used as the test set. The others are the training and validation set. And you do this in turn. So, first turn, the first fold is the test set, and all the others are training and validation. Second turn, the second fold is the test set, and the other are training and validation. Okay, this became the best practice, and this is used. The terminology may be a bit overlapped, but this is what we take as a test set in these k-splits. Okay, so the k-fold cross-validation is a procedure that is used for model selection, okay, to decide the best model. Once I have found the best model, I still have to test the model on completely unseen data. Okay? The procedure is obviously repeated k times until each and every fold has been used as a test dataset for validation, not as the actual final, let's say, test on unseen data. as I said, this procedure is the gold standard for doing validation. There is a bit of a problem with this procedure. It is not entirely trivial to calculate the performance metrics that we have seen. Why? Well, because if we have threefold, for instance, cross-validation, just to keep it simple, basically any run can give us different measures because we are using different mixes of the data, okay? Some data for training, some data for validation. And we will have the metrics, the confusion matrix, so the accuracy from these metrics, as I said, you can derive the accuracy, the precision, the recall, the F1 score, the ROC curve, the PR curve, whatever. You will have basically one confusion matrix for each of the folds. If you do threefold validation, you can have three different confusion matrices, okay? That's fine, because we are using different data for training and different data for validation. The whole data is the same data set, but we are mixing together in different ways. So basically you have to make a choice, because at the very end I want to give a score, a performance score to my model, not to each of my k-fold validation runs. So basically you need to choose how to aggregate the different confusion metrics. And it happened before. This is another case in data science in which there is not a best answer, okay? It really depends on the data set, on the characteristic of the data, whether it is balanced or not, for instance, so it really depends. So when you can, do both, and usually today when you can, you always can, because there is a software library that does it for you. The two possibilities are what is called macro averaging, which means compute the metric for each of the folds. Okay, so I compute the precision, the recall, the F1 score, the accuracy for each, and then I take the average. Okay, simple plain average. Accuracy of this fold, accuracy of this fold, accuracy of this fold, average accuracy. That is called macro averaging. The other alternative, obviously the only other one, is sum everything and compute the statistic, the precision, the accuracy, the performance measure on the summation. Okay, so sum all of this stuff, obtain a single confusion matrix, and compute your statistic there. Okay, that's the other alternative. They can be different. They usually are different. If they are exactly the same, usually it means that something was wrong in the validation. Simple example, this is just random numbers, but with these numbers, the macro precision will be 0.667, the micro precision will be 0.727. So it can be quite big, okay? This is half, okay? A decimal is quite big in this case, because obviously these kind of measures go from 0 to 1, so you don't have so much space. But again, there is not actually a general rule for choosing macro or micro. It really depends on the specific domain. All of this kind of stuff we will see in practice. We can get them done, obviously, by a software library. But you need to know what is behind these measures, okay? For the same reason I told you before. If you read a scientific article that gives you only one or two of these measures, be skeptical. Because the precision, for instance, only tells me how am I good at predicting, for instance, the positive event. The precision alone doesn't tell me anything about how I may be bad in predicting the negative event. Nothing. Okay? Even the recall. the recall again only tells me of all the correct positive, the one I spotted. But it doesn't tell me anything about the actual negatives, okay? And in a sense also the accuracy to some extent. So all of these measures should always be given together because they measure complementary things.